The remaining two dimensionless number will be discussed on this slide. The first one is Rayleigh number. So Rayleigh number is governs natural convection phenomenon. This is basically the product of Grashof number and Prandtl number, and it is critically important number in case of natural convection phenomenon, which determines which type of flow regime the natural convection is happening, whether it is natural, whether it is laminar or turbulent. Next number of critical importance is Reynolds number, which is ratio between inertial force and viscous force, and it is given by this particular ratio, which is rho VL by mu. Now let us move ahead with a thermal boundary layer phenomenon, or the concept of thermal boundary layer. This slide will go into depth of that particular concept. Now the thermal boundary layer concept is analogous to viscous boundary layer, and it is a similar concept happening in case of heat transfer, which is very similar to the phenomenon called viscous boundary layer, which we have already studied in our earlier course. Now thickness or height of thermal boundary layer is dependent on fluid flow. So in that case, it is also a function of temperature difference as well as fluid flow. And Prandtl number is a non-dimensional number to judge whether the thickness of thermal boundary layer is greater than or less than the viscous boundary layer thickness. So if Prandtl number is high, thermal boundary layer thickness is much less than the viscous or momentum sublayer thickness, and if Prandtl number is low, thermal boundary layer thickness is much larger than the momentum or sublayer thickness. In this particular image, we'll explain in detail the concept of thermal boundary layer. This is a plate at temperature Tw or surface at temperature Tw, over which there is flow with velocity u, and temperature of the ambient is T infinity. So this image shows the concept of thermal boundary layer in comparison with the velocity of the viscous boundary layer. As you can see, this is the surface at temperature Tw or wall temperature, and there is fluid flow happening over this surface at u velocity, that is the bulk velocity u, and bulk temperature T infinity. And as the flow goes from this point to some path ahead along the surface, the temperature of the fluid goes on changing. So as you can see, this is the temperature of the fluid given by Ty, and this is the height of that particular temperature or thermal boundary layer. So this is the temperature profile. If you can see, as a function of the height, this is how the temperature is varying. The fluid that is in contact with the surface is having Tw temperature, and as it goes away, the temperature reduces to the bulk temperature, and this is the rate by which it is basically moving. That is the velocity boundary layer. As you can see, this is the velocity profile, and this is the blue one is basically the thermal boundary layer, which means as the temperature is changing from T wall or T surface towards the bulk temperature T infinity. And so the thermal boundary layer gives the description of that, and this is the velocity boundary layer. In this case, the velocity boundary layer thickness is less than the thermal boundary layer thickness, which by our definition means that the Prandtl number is low. So our thermal boundary layer thickness is much larger than the momentum or velocity boundary layer thickness. So let us now go ahead and discuss the heat transfer coefficient concept in detail. Now, heat transfer coefficient by definition is basically a measure of the ability of a material to transfer heat per unit time, given 1 unit area of the material and temperature gradient through the thickness of the material. It is not a property of the fluid, it is a property of flow, and experimentally it can be determined by parameters whose values depend on convection phenomenon, surface geometry, nature of the fluid motion, properties of the fluid, and bulk fluid velocity. So it is a function of all these parameters, not just a single function of or a material property. H can also be a function of temperature, and in case of natural convection, it is if you can see, it is related to the gradient of temperature to the power 1/4 or 1/3, and in case of forced convection, it is a function of temperature gradient only, no exponential power, and in case of boiling phenomenon, it is a function of temperature gradient raised to the power 2. Let us discuss natural convection phenomenon in detail. Natural convection means in that case the fluid motion is due to buoyancy effects and the heat transfer is due to fluid motion, but the fluid motion is only due to the buoyancy effects, that is density gradients, because of heating of the fluid. And underlying phenomenon is basically as the fluid temperature increases, its density increases. So if the fluid is in contact with some hot surface or hot temperature region, its temperature goes on increasing, its density goes on decreasing. Density gradient results in buoyancy force. So the hotter fluid, as the density decreases, starts to rise up. Gravity force is opposing the buoyancy force. It is trying to push the colder fluid down, and we get sort of a net buoyancy force, and which is given by the difference in density into gravity. Rayleigh number is critically important in that case, which is given by this particular ratio, which involves gravity, the temperature gradient. And if you can see, this is the pictorial image of the natural convection phenomenon. As you can see, as the temperature of the fluid near the wall is increasing, the fluid starts to rise up, and there is a sort of a thermal boundary layer which is developed like this. Also, because of this thermal boundary layer, there is velocity induced in this particular domain, and you can see this is how the motion is dictated by the velocity profile because of natural convection. There are natural convection currents that are developed. So going ahead with our discussion on forced convection, this is convection heat transfer results from fluid motion, as we discussed before. Heat transfer rate can be closely coupled with the fluid flow solution. So even in CFD codes, the interlinking between fluid flow solution and the heat transfer equations is strong when we are solving for forced convection. The rate of heat transfer is strongly dependent on fluid velocity and fluid properties, and there are empirical relations also for the same. We have fluid properties which may vary significantly with temperature. So in convection heat transfer, the heat transfer coefficient on which the forced convection rate depends is also dependent upon change of fluid properties with temperature. And whenever we have cold air flowing past a warm body, it draws away warm air near the body and replace it with cold air. An example that was an example on forced convection. Next convection mode of heat transfer, which is somewhat different from the standard forced convection or natural convection and heat conduction, is basically boiling. So what do we mean by boiling? Boiling is actually fluid phase change, and the heat transfer occurs during the phase change. This is also a convection mode of heat transfer, and it involves fluid motion, and boiling occurs at solid liquid interface. An example of a boiling fluid is shown here. It is basically highlighted by a strong formation of vapor bubbles at solid surface. The bubbles grow and detach from the solid surface as shown here. Large heat flux can be achieved with a relatively small temperature difference in this case, because there is phase change and that latent heat change is also considered. Heat transfer is given by basically there is temperature difference, that is from surface temperature and saturation temperature, and heat transfer coefficient is a function of this particular temperature gradient, as well as heat transfer coefficient and properties like Cp, K, mu and sigma. And we also have the heat transfer rate, which is dependent on H and delta T. So this is a sort of a phase change diagram for boiling heat transfer, and we can see different regions of boiling heat transfer process in this particular phase change diagram, which is heat transfer rate versus the temperature gradient, that is the surface temperature minus the saturation temperature. And as we can see here, as the temperature gradient goes on increasing, we have free convection in the earlier part where the temperature gradient is from 1 to 5. And after that we have basically nucleate boiling phenomenon starts, and here we have isolated bubble formation in which the heat exchanges through direct transfer from the surface to liquid motion, not through the rising vapor bubble. And after that we have jets and columns region, in which the densely populated bubbles induces liquid motion near the surface. So this happens within the nucleate heat transfer. After nucleate heat transfer, we have a transition boiling where the heat transfer rate decreases slightly, and once after this point, the heat transfer rate again increases within the film boiling region, in which the surface is completely covered by vapor film. Heat transfer is from surface to liquid and conduction through vapor, and hence we get higher heat transfer rates over here. So this is the entire phase change diagram for boiling heat transfer. Let us see boiling in comparison with evaporation, which is also another mode of heat transfer. Liquid to vapor phase change process is similar to evaporation in case of boiling. In case of evaporation, the the liquid to vapor phase change occurs at liquid vapor interface when the vapor pressure is less than the saturation pressure of the liquid at a given temperature, whereas in boiling the liquid to vapor phase change occurs at the liquid at the solid liquid interface and not the liquid vapor interface, but it occurs at the solid liquid interface when the liquid is brought into contact with a surface which is maintained at a much higher temperature Ts above the saturation temperature of the liquid. So this is the distinction between evaporation and boiling heat transfer.